Okay, so now finally we're getting to public key cryptography. We're getting to RSA and something called signatures. Um, so as I've said a couple of times in symmetric cryptography, the two parties that want to communicate, they need to have the same secret key. And encryption and decryption use the same key, and this is fast and secure, but key distribution is of course the main drawback. In the 1970s, there was a revolution by Hellman, Merkel, and Diffie, and this is called public key cryptography. Right. So here, as we talked about yesterday, everybody has both a private key and a public key. And in order to, so if Alice wants to send a message to Bob, what she has to do is she has to use Bob's public key in order to encrypt. And then the only way to decrypt is then using Bob's private key. And the analogy is padlocks, because anyone can take a box and close it with a padlock. Only if you have the key that matches the padlock can you then open the padlock again. And the great advantage is, of course, here you don't need to transmit any keys. So even if you never met someone before, you can communicate securely if you encrypt using their public key. Why is this not the only type of encryption that we use? Why do I keep saying that we still use AES? And well, the main drawback of public key crypto is that it's a lot slower than AES. So then what we do in practice actually is that we use public key encryption to share securely the secret key and then use the secret key for symmetric encryption. Okay, so then how do we get this? How do we get these public key encryption schemes? How can this be mathematically possible? So we need what we call trapdoor one-way functions, and those are functions that are easy to compute one way, but hard to compute the other unless you have the key. You want functions that are easy, where you mean it needs to be easy to compute the function one way, i.e. it needs to be easy to encrypt. It needs to be hard to compute the function in the other direction unless you have the key. So it needs to be hard to decrypt unless you have the secret key. So here are some examples of maybe trapdoor, maybe one-way functions from modular arithmetic. So yeah, one of them is a one-way function and the other one is a trapdoor one-way function. So one way, it's an easy problem. If you have a, b, and n, then you can calculate a to the b modulo n. This is an easy calculation. It requires a lot of multiplications and reductions, of course, modulo n, but this is something that you can do fairly efficiently. The hard problem is then to go the other way. And there's actually two hard problems that comes from this. One is if you're given a, and you're given a to the b mod n, can you then find b? Can you then find the power that a must have been risen to in order to give a to the b mod n? That's one. This is actually a hard problem. The one that we'll use as a trapdoor, the one that has a trapdoor, the problem that's sometimes had is the discrete root problem. So here you're given the power, and you're given b, and you're given a to the b modulo n, and then you need to find a. So then you need to find out what do you need to raise to the power b in order to find n. So I call this the discrete root problem because if b is, for example, 2, then this is the square root problem, the discrete square root problem. You're trying to find a number so that it squared is equal to some known number. So that's the square root problem. If but b doesn't need to be 2 here, it could also be 3, for example, then it's the discrete cube root problem. You're trying to find a number so that if you cube it modulo n, then you get something known. So in general, I call this the discrete root problem. And what is going to give us a trapdoor for this problem is the problem of factorization. So the integer factorization problem is the following. given some integer, compute its decomposition into prime factors. So calculate the prime decomposition of, so given an integer, write it as a product of primes. And this is of course always possible. We know that from number theory, but trying to find the exact primes can be very hard, especially, I mean, in particular if n is big. And the n's that are used for cryptography, they have more than 2,000 bits. You need more than 2,000 bits in order to represent them in binary. And actually, if we can, and then what gives us the trapdoor for RSA is that we can solve the discrete root problem if we can factorize n. Okay, so actually you can break RSA if you can factorize, but luckily factorization is hard. So in order to have the trapdoor, what you do is then when you decide your public key, then you just decide on the P and the Q, and then you multiply them together, and then you make the N publicly available. Let's see this in more detail. Okay, let's first do a little bit of history. RSA stands for Rivest Shamir Edelman, and RSA was invented in 1977. It's the first public key crypto system, and it's asymmetric crypto system based on the discrete root integer factorization problems. Okay, so how does it work? Okay, so in order to generate a key in order to generate the secret and the public keys in RSA, you choose two prime numbers, P and Q, and you compute the product. And then you compute something that we're going to call a lambda of n, which is just the least common multiple of P minus 1 and Q minus 1. The least common multiple is the smallest number that both P minus 1 and Q minus 1 divides. Then you choose an E, which is co-prime to lambda of n. And then you compute the inverse of E modulo lambda of n, and you call that T. We talked about inverses yesterday, so if you're in doubt about inverses, go back and rewatch that. And then you call the public key is then going to be E and this capital N, and the private key is then going to be E. So notice that in order to, so if you're just given E and N, then we're assuming that that factorization is hard. So we're assuming it's hard to find P and Q given just N. And without P and Q, actually, it's hard. It's a hard problem to calculate lambda of n, because in order to know lambda of n, you need to know P minus 1 and you need to know Q minus 1. But if you don't know P and Q, then you don't know, if you only know n, then you don't know P minus 1 and Q minus 1. So in this case, where you only know n, but not the factorization, you can't compute lambda of n, and therefore you can't compute P, because you need to know what modulo you have to calculate in order to find the inverse of E. Or what inverse of E modulo what number. Right. So in that way, the private key can only be computed if you know the factorization of n, or that's at least the security of RSA. And of course, I guess, of course, as with any crypto system, we only believe it's secure because no one's managed to break it so far. But RSA really has been investigated for a long time, so it seems we feel quite confident that it's not possible to compute P without prime factoring in. Okay, so now that we've set up all this and we've convinced ourselves that even given the public key, it's a hard problem to find the private key. How do you then encrypt and decrypt? Well, the ciphertext, in order to encrypt with RSA, you take the message that you want to encrypt and you raise it to the power E, calculate this modulo capital N. And this, of course, you can do if you have the public key, right? Then you choose the message and you know E and N, so you can calculate this, and then that's going to be your ciphertext. And then the decryption. This might seem quite magical at first, but we'll get into more details with this. In order to compute the message given the ciphertext and the private key, all you have to do is actually take the ciphertext and raise it to the power P, and then you get back the message. Of course, in order for any of this to work, you need your message to be a number, and you need it to be a number that's between 1 and capital N. So I mean, so in practice, if you have a message, that'll often be, you know, a character string. Then you convert that message using, for example, ASCII. That gives you a number, and then you encrypt it using a scheme like this. If your message is too long, then you need to chop it into bits, into parts, and then you encrypt each part separately. So just to take an example, let's say P is 61 and Q is 53. Then N is going to be the product of the two, 3,233. Lambda of N is then going to be the least common multiple of P minus 1 and Q minus 1. That turns out to be 780. E, I mean, I can pick it in any way I want, as long as it's co-prime with lambda of N. Co-prime meaning that one is the only number that divides both of them. So I mean, E can't, for example, be even because lambda of N is even, and if I choose E even, then, you know, E and lambda of N wouldn't be co-prime. They would share the common factor too. D is then calculated as the inverse modulo lambda of N. And I mean, for this, there exists, as I said, there exists fast algorithms, but actually what I mean, here I'm not going to go into details with how these algorithms work. So what you might do is you might use Wolfram Alpha is what I actually usually do. It's a web page. Type in inverse modulo, and then it just gives it. Otherwise, you can use Python's function. Python has a function called pow, and for that one, you just give the number, and then you give the exponent, and then the modulus. So in order to calculate P here, for example, you would say, I want 17 to the power minus 1 modulo 780. And that would give you, then this function would return 413 to you. Okay, so now we've set up the public key and the secret key. So let's see encryption happening. Imagine we have this message. The ciphertext is then the message raised to the power E. Again, this you can calculate using Python, for example. And to go the other way, we take the ciphertext. This is then the ciphertext 2183, and you raise it to the power T, which is 413. And then you get back the message. And again, for now, this seems like magic to you. I'm sure, like, why does this work? And as I said, I do want to go into more detail with how it works. But I think before we do that, I want you to try to do this encryption and decryption. And before, okay, so let me just say this. So example of an N, which might be used for RSA. You want N to be very large, because if N is not large enough, then it's not hard to prime factor it. The larger the number you're trying to prime factor, the harder it is to factorize it. So this is an example of an N that might be used for RSA. And RSA is the reason why cryptographers care a lot about big prime numbers, and there's a lot of research into the structure of prime numbers. Okay, so cryptography is not the only reason why there's research into prime numbers. Prime numbers are just like interesting objects in themselves, and mathematics mathematicians like that, right? But they are also very useful for cryptography. So now an exercise for you. So I give you a message. I give you a P and a Q and an E. And I want you to try to calculate P, which is the inverse of this E, modulo lambda of N. So you need to calculate lambda of N. And then I want you to try to encrypt this message using these parameters. And then afterwards, try to decrypt it and check that you get the message back. So I will do a little dance while you pause and try this out for yourself. Okay. I hope that went smoothly. I'm sorry you have, I can't show you both slides at the same time, so you're gonna have to open the slides to see to have both the numbers and the previous example to compare. But I hope that went smoothly, and you can see that if you did it right, then you get back the message, and if you did it wrong, then most likely you don't get back the message. So you should be able to check your own work that way. Okay. So now we get to a bit more technical part. Now, why does this work? Why is it true that if I take my ciphertext and raise it to the power d, where d is the inverse of e modulo lambda of n, why do I then always get back the message, right? This is magical in a way. So in order to understand this better, I want you to just see some examples and see how this works. So I remind you of the discrete root problem. We have e and n, and we have m to the e modulo n, and we want to find the message m, right? So this is actually the decryption problem, right? Given an encrypted message, this is how you encrypt. How do you get back the message? So here, what I've done is I've chosen a specific n, capital N. I've chosen capital N equal to 7. And then I have different messages here, and I have different powers here. So 0, for example, let's just take this row. So if I take 0 and I raise it to any power, I'm always going to get 0. If I take 1 and I raise it to any power, I'm just going to get 1. However, like for example, if I take 2 and I raise it to different powers, like 2 to the first is just 2, 2 squared is 4. 2 cubed is 8, which is 1 modulo 7, and so on. So I hope that it makes sense to you how this table is generated. Now I want you to just take a moment and then see what patterns emerge in this table. Yeah, think about that for a little while I dance. Okay, so of course there's many different patterns that you might see in this table. The one that I'm hoping that you see is this column. Okay, the easier one to see is probably that this column here consists of all ones. And this column here, again, consists of all ones. And actually, like every column that's divisible by 6 is going to be all ones. And the reason why this happens is this, in order to move, you can see all of these lines, they're repetitive. Once you hit here, then like this part here is just a repetition of what you had over here. And why does that happen? Well, it's because in order to get 3 to the power 7, you can calculate that as 3 to the power 6, which is 1, and then multiply by 3, so that's 3. So therefore, you get exactly the same if you start here or if you start here and just keep multiplying by 3. But each step here, I'm multiplying by 3, and once I hit 1, then the pattern just repeats. So this is an argument why every column that has a number, so at least now we see that every column that has a number that's a multiple of 6, here I'm just going to have the column 1. Okay, and 6 is actually lambda of n, because if I prime factor my n, the prime factorization of 7, that's just 7. And then if I take the least common multiple of the prime factors, the minus 1. So remember, lambda of n, here I need the prime factors minus 1, and 7 minus 1 is 6, right? So 6 is actually lambda of n. So the magic is happening at lambda of n. And actually what's happening is the next column is actually the one that we're going to be using, because the next column here, we just have m. Because remember, this column here is just this column here multiplied by m. So here m to the power m to the power of 6 times something plus 1 is going to give us m again, because m to the power of 6 times something without add 1, that's just 1. And then the next column, then I get m again. And actually this, yeah. So, all of these columns here, like 7, 13, the next one is going to be 19, 18 plus 1 is 19, and so on. All of these columns, I'm just going to have M. And this is what I'm going to use for decryption. So let's see this in an example first. So imagine that my E is now 5, then C is M to the power 5 modulo N. And if I then decrypt, in this case, the inverse of 5 modulo 6, that's again 5, because 5 times 5 is 25, which is 1 bigger than 24, which is divisible by 6. So the inverse of 5 modulo 6 is 5. Therefore, in order to decrypt my message, in order to decrypt my ciphertext, I raise it to the power 5. And now let's see the magic happening. Raising my ciphertext to the power 5, well, that's the same as, so my ciphertext is just m to the 5th, and m to the 5th, and then to the power 5 again, that's m to the 25. I hope you agree. And m to the 25, I can write that as m to the 6 times 4 plus 1. And we just agreed, I hope that every time I take m to the 6 times something plus 1, then I get just m, and therefore I get just m back. The magic is the reason why raising to the power d is going to work is because, so like what's happening up here in the power is here we have d times e, and since d times e is 1 modulo 6, because d is chosen to be the inverse of e, so therefore the product of these two is going to be 1 modulo 6. And therefore, I'm going to end up in one of these columns that's just one after a column that's all ones. And that's why we choose D as the inverse of E modulo 6, not modulo 7. In the exponent, we're calculating modulo 6. Let's see another example. This one is a little bit harder to see. Because here n is 10, and the pattern is easier to see when n is a prime. But have a look at this n equal to 10 and see if we might still be able to do something similar like before. I'll do a little dance, and you can think about it. Or maybe go back and revisit and then come back and see if you can find a pattern in this table that will help us do a similar trick like before. Okay. And so now what we see here is that it's no longer so that there are any columns that are all ones. That's just no longer true when n is no longer prime. However, n is 2 times 5, and lambda of 2 times 5, let's have a look again. Lambda of 2 times 5, that's 2 minus 1. The least common multiple of 2 minus 1, that's just 1. And 5 minus 1, that's just 4. So the least common multiple of 1 and 4, that's just 1, that's 4, right? So lambda of 10 is 4. So we expect something to happen in all the columns that are 1 bigger than a multiple of 4. So here we have the column 5, that's 1 bigger than a multiple of 4. And here we see exactly the same pattern as before. Here we're getting just the message back again. And here the next one, 9 is 1 bigger than a multiple of 4, and here we see it again. 13 is 1 bigger than a multiple of 4, and here we see it again. So exactly the same thing is happening. We're calculating modulo lambda of n in the exponent. We calculate modulo lambda of n in the exponent. So here modulo 10, if I take m and raise it to 4 times something, plus 1, then I get back m. And this is true for all whole numbers k. And here, just to reiterate, 4 and 4 is, and how do you know that 4 is an important number? And that's because 4 is lambda of 10. So let's again see this in an example, how we can use it to decrypt. And here I choose my e equal to 3. And here I don't have so many choices, right? Because I mean I need to choose something that's co-prime to 4. So I can't choose, I mean, choosing 1, then I am not doing any encryptions. And I can't choose 2 because 2 and 4 are not co-prime. I can choose 3, and 3 is actually my only option for encryption exponent. So I choose that. So this is going to be my ciphertext. And if I then decrypt, then I mean, here again, D and E are equal, and like ideally, I would have wanted an example where D and E were different to show you that that might happen. And in general, like it's very unusual that D and E are equal. It's just that in these very small cases, there's just not a lot of choice for D and E, and therefore they often end up being equal. But like as soon as you get bigger n's, then like it's unusual for them to be equal. But here D is equal to E, and it's equal to 3, and that's because so 3 is its own inverse modulo 4. Because if I take 3 times 3, that's 9, which is 1 modulo 4. It's 1 bigger than 8, which is divisible by 4. So D is 3. If I take my ciphertext to the power 3, then I get the same as if I take my message and raise it to the power 3 and then raise that to the power 3. So this is my message to the power 9. And again, 9 can be written as 4 times something plus 1. And we know that the message to the power 4 times anything plus 1, that's just the message again. So here we just saw the magic again. Because D and E are inverses modulo 4, and because 4 has this magical property up here, that's the reason why when I take my ciphertext and raise it to the power D, then I get back my message. Pretty cool, huh? Right. That was all I had to say for plain RSA. Let me pause. Let me stop the video here.